So you remember before when we talked about index refraction that we said that we had some probability amplitude for the electron to be around the nucleus in the material, and if you applied an electromagnetic wave like a light wave, this would oscillate forward and back, and from this we would get emission. So when we came in with some light, that would cause the electrons to oscillate, and they would emit radiation. And previously we looked at the case when we have fairly weak incoming electromagnetic radiation, and then the response of the electrons are linear. And since it's linear, that means that they are doing a sinus wave, and this sinus wave only contains the original incoming frequency. So the light emitted by the electron clouds moving will have the same frequency as incoming light. So this is not frequency doubling. But if we start turning up the intensity of a light, at some point the electron cloud cannot move freely. I mean, this is a very, very simplified model, but in principle there is something which makes the response of electron cloud non-linear. So we can this is an extreme case of non-linear response. We have here a square wave. So let's look at the frequency content of a square wave. So that's the same thing to say as we will try to express a square wave like a series of sinusoidal waves. And then we start off with the fundamental frequency, which you have at the top here, which in the frequency scale is at 1 in some unit. Let's say call it 1 Hertz. And then the first overtone, when we want to describe a square wave, is this one here, which you see here is at 3 times the frequency of a fundamental frequency. So that's up here, and then the next one, that's at 5 times the fundamental frequency, and the last one here at 7 times, and then we go on 7, 9, and so on. But the interesting thing is a square response like this, a symmetrical square response, that does not contain any component at the double frequency. So you can actually not use a symmetrical potential to generate some frequency, do some frequency generation. So instead, so here we have written out it. So the square wave then depends on the fundamental frequency, and then 3 times the fundamental frequency, 5 times. But if we take a non-symmetrical wave, like example a sawtooth wave, this is an inverted sawtooth wave, then it contains the fundamental frequency, 2 times the fundamental, 3 times, and so on. So if we have potentials, which means that the electron move in a way which is non-symmetrical, we can use that for some frequency generation. We could of course use something with a more squarish response, a symmetrical response, to do frequency tripling. That would be possible. Okay, so let's move on. So if we now have something with a potential which is anharmonic, non-symmetric potential like this, and we come in and the electron moves like we see here. So we're driving it at fundamental frequency, which is the blue one here. But if we want to express this response as a series of frequency, we also need, well, this is only the first one. This is the second, the double frequency. So the blue one here is shifting frequency twice as often. That means that the light coming out, if we drive it hard and has a response like this, contains also the double frequency. So that means that we can do some frequency or double frequency generation with a crystal like this. The red one is just optical refraction. If you drive a crystal like this hard, it will turn out that you also get a DC term, and that's the red term here to explain the movement. So what kind of materials behave like this? Well, a very popular material used is a crystal called lithium niobate. And if we go above its ferroelectric Curie temperature, so above 1200 Celsius, it's in a state called paraelectric phase. And in this paraelectric phase, the lithium ions here, let's just look at the lithium ions for the start, they are symmetric around this oxygen plane. So that's drawn here like a line, and the lithium ion sits symmetrical, and the lithium ion here sits symmetrical. But as the crystal cools down and shrinks, this moves. The lithium ion will have to move. So at a colder temperature, the lithium ion sits slightly unsymmetrical like this compared to the oxygen. And this creates this non-symmetrical crystal where the electron response when you drive it hard has a non-symmetrical response, just like we talked about before. So we then get this kind of response. Now, just as a quick note, if you ever heard of periodic poling of lithium niobate, that's when you apply a very strong electric field so that you force it into one state or the other. So if you apply a field in one direction, a very high voltage across the crystal, you will actually make it deform like this. And if you were to apply a very high voltage in the opposite direction, it would instead force the lithium ions below the oxygen plane. And that means that you can actually choose the phase of a generated light here. You can flip the phase of a generated light 180 degrees compared to the incoming light. Anyway, I won't go any further into that, but both of these you can actually control how you want your crystal to which way your crystal should look.